then we found some people that were genuine humans and very generous that gave us the opportunity to invest some serious money, and that includes myself as well, to build the first continuous plant in Terramutu. That has been decommissioned now because all the tests and everything is finished. In the meantime, the rights for India are sold, and as we speak, the first commercial plant is going up in Hyderabad with a capacity of about 32,000 tons of in-feed of used tires to produce carbon black. That carbon black is then utilized either going back into the tire industry, going into carbon fiber industry, or going into printing ink, because the tinting strength of this carbon black is stronger than cracked acetylene, which is pretty significant. But coming back, in New Zealand, we know that the best part this year of 22 million cubic meters of roundwood pine has been exported off the country, which reflects on an efficiency rate of 65% of logging companies, that the best part of 9.5 to 10 million cubic meters of slashings are left behind, merely producing CO2, aciding soils, but more than this, how shall I say, breeding bora. So congratulations to that. Now this particular material is highly sought after in the market in Europe at the moment. Reason for that is very simple. Europe bailed out of nuclear energy. They are decommissioning plant after plant. On top of that, have introduced a hefty carbon tax on fossil fuels. As a result, the energy market over there is hungry for something that is carbon neutral, and so we've exempt from carbon tax. Now, New Zealand is far away from Europe, so transport costs are immense. As a result, we have thought of sweetening a product that withstands the higher transport costs. So if we have thought, okay, if we produce our carbon black out of the slashings and put about 10% of this carbon, which is pure carbon and runs on about 42 to 45 megajoule a kilogram, into torrefied pellets, we lift the calorific value of this particular pellet by about 25%, which makes more than likely up the transport cost difference to Europe. I understand this is only a temporary solution for the next 15 to 20 years, but tell me something better. So as a result, I had a meeting today, and I can now safely say that we have secured fundings to put the first commercial plant in New Zealand up within the next 18 months. So we will have a significant amount of biocarbon available. I understand, and I think you will agree, that this is a waste of this particular material, but I consider it as a vehicle to subsidize in a way to en masse produce biocarbon suitable for horticultural industry. It's like everything, you have to have the milking cow to feed the calf. So this is where we sit. Anyway, just try to give you a few images here, if I can get this thing working. I'm totally yeah. Okay. Try whatever you do. So this is just, it's all blah blah, and what I want to get down to is this is, for example, we have a chestnut here, prior and after the process. This is what can be done. Now, this is a 1 in 1 million magnification of a piece of char produced with this technology. So you don't need to think twice what the surface area of this is.
What is the feedstock?
That was
that
was Pinus radiata.
Yeah.
So, particularly the material we're talking about. So, anyway, so this is a tire prior and after. You've got the carbon black, you've got the steel falling out, and you've got a little bit of petrochemical liquid left that you can fractionize, hydrogenize, and use it as a fuel. It's a process image, but this here is by far more interesting because this is actually the 3D layout of the plant that apparently goes up in Hyderabad. So, the process is largely emission-free, and well, Barry explained it before. I don't need to tell you why, because it's very simple. We are capturing volatile, we're utilizing volatile, what we send out is CO2. And with this particular unit, we have something in addition, because we're actually chilling the exhaust of our afterburners and send it through compartments where we have product stored in. Now, since this product has an enormous surface area, it absorbs some of the C in the CO2. So we are reducing the emissions even further by increasing the carbon yield in the material. So then we've done some tests, and here comes the interesting part, because this is the first time you see the contraption where it all started. That's in front of my garage. What we've done is some general waste, organic, inorganic mixing. This is only a demonstration that the technology works on regardless what the basic material is, as long as it carries C and H. This has no value on product because it's rubbish, and I can only confirm what Barry says: rubbish in, rubbish out. That's it. So you have to know what your application is, and then you can consider your appropriate feedstock. Now, this is closing the unit and heating it up. The key difference between what Barry is doing and what I'm doing is I was always aiming to capture every possible volatile matter. So you will see the base plate of this is about 40 millimeter solid steel, and so is the rest of the reactor. The reason for that is because it's an enclosed pressurized system. We're working on serious pressures, and if you are familiar with physics, you will understand that if you have two linears, one is temperature and the other one is pressure, and you elevate them, eventually they meet a point. And once they meet the point, this is when you create a reaction. Okay. Once you create that reaction, it's not so much actually keeping that reaction going, it's controlling it or trying to prevent it from getting out of control, because if it gets out of control, it's a bit of a problem. So, and this is the result. Basically, you have your char coming out. This is while it's still sitting in there. You will realize that it doesn't change much of the actual physical geometries, but it shrinks considerably because you're pushing out moisture and volatiles. So you're left over with a skeleton. I think the simplest way to explain it is if you consider your body, you've got blood, flesh, and bone. What you do here is, because it happens so rapidly, you're pulling the blood away, you're pulling the meat on one side, and you leave the skeleton. The skeleton is the carbon. Now, what it does is, because it happens so fast, and we could call it activation, it has a desire, as soon as it comes out of the reactor, to grab something, and it grabs whatever it can get hold of fastest. So if I take this stuff, for example, and put it into Waikato River, what does it take? What is free available in the water? Phosphates and nitrogen from our nice stereo farm. So, if I put that in a bag of Kevlar, submerge it in the river, let it there till it's saturated, I have phosphate and nitrogen enriched char. Then comes Mr. Alf and Mr. Rob Hill, of course, and put some nice fungus into it that locks that thing in such a way that water cannot leach it out anymore. Sequester it into soil. What do you get? It's a long-term organic fertilizer. Would you agree? Yeah. Okay. Now this is an interesting test. This is material here that I was given from a plant in Chapel Road in Tauranga, where it stinks very much because it's the water treatment plant. So this is sewer pond sludge. Mix that with a matrix of half decomposed pine waste. Put it in. What you get. So mix it. Lovely. Put it in. Let it go. And here it comes out. This here is a biochar of low value because it carries an enormous amount of heavy metals and some poisons. Detergents are not really friendly if they come. Anyway, but what you can do with this is there's a standard to sequestration. But for the forestry industry, for example, if you mix this in a certain ratio with composts, other biochars, to get the concentration of heavy metals and toxins down to a level where it's fit for sequestration. I think with New Zealand forestry you can't do much wrong by applying this, because what boron, copper spraying and so on does is probably a little bit more dangerous than what we have. So this is basically what we're doing on the bio side here. I think if I can, because again this is how can you open those blimmin' pictures?
Highlighting the spacebar.
Okay. Ah, yeah. Where's my proud moment? Okay. So this is me with the shovel taking the first carbon out of the first continuous plant in Mutu. Can we? Ah, it works! Wow. Fascinating world of technology. Sorry. So this is how this beast looks like, and yes, it's great that you can see so much of it. So this is the infeed, more or less. We've got a hopper here with a boat winch, so we can lift the lid, and we chuck some material on the top. Then we have a device that pushes it into the plant, and yep, this from the back side. So what we do here is basically pushing material into the reaction zone. What you see here is gas purification and then volatile gas collection for the afterburner. That's inside of the beast. It's the heating zone. It's about 7 meters long. And this is basically what you see here is waste pulp from Noskiskog in Kavra, carbonized. They only bury about 70,000 tons per annum in their landfill. So, yep, and here comes it out. It's nice and black. So all I'm trying to explain here is that I have very little. Well, Alf gave me some certain information what it can do in the agricultural, horticultural system, but you understand that technology is available to produce it en masse. That's A. B. This would bring production cost into a frame where it's more or less equal to an artificial fertilizer such as urea. And it has some certain benefits that because before I came to New Zealand, one of the largest projects I was managing was the largest phosphate mine in the world in Jordan, producing 3,000 tons of grey phosphate for the agricultural industry per hour. So, and I see what we're doing to our planet, and this is why I'm standing here, because I cannot possibly allow myself to have this going on. We have to do something. We have to do something to make this country sustainable. Our farming industry is killing us. but unfortunately you're not allowed to say it because there's a bit of money behind it. But it is possible to change this. I think we've made the first steps in this direction, and let's hope that the people that I'm talking with in the moment are sticking to what they promised. If they do, I can assure you that in about 18 months we're going to see something in New Zealand that will help us in the long run very much. So if you have any questions to this technology, just please let me know, because there's not much more I can say. All I can say is I have the technology and it is commercialized, so it will happen regardless.
What is your heat source?
My heat source, my initial heat source is electricity, plain electricity. I needed to bring the material up to the moment it reacts. From the moment where it reacts on, I'm using volatile matter to superheat. What happens is, and Barry made it quite clear, there's a syngas emerging. Now, in my case, I've got something on top and I've got a hell of a lot of steam on biomass. So my steam syngas combination goes into a turbo that drives a generator. Now that's a condensing turbo. So my steam drops out with a little bit of bio-petro, if you want to say so. That swims as a film on top of the water, so you can skim it anyway, and leaves the combustible gas or the combustible portion of the gas free to go into an afterburner to create heat in a superheater step on the reactor. Then, after creating my heat, I'm pulling the exhaust gas into a chiller and into a compactor and re-inject it into the product chamber, which gets constantly exchanged. And on top of that, I'm re-injecting some of this gas on the feed end, as it is a continuous process, okay? Because what I do is I basically create some slight overpressure from the product end as well as from the feed end. First of all, I don't want to have a reaction going on in my feed chamber because yeah, we all know why. I have my fingers and equally. So what basically I utilize that to create a slight overpressure to always hold oxygen out of the system. What I've done is nothing new. All I have applied is a certain technology to make sure I can run a continuous process, which means I do not need to ramp up temperature, chill down product before I take it out. It goes through. Hence the capacity of such plants. So
are you open sourcing this for
commercialized? Once it's commercialized, I might open source it, but not at this very point of time. It is not in the interest of my two business partners, nor is it in the interest of the people that are involved in the moment to commercialize this. So, unfortunately, I have to say I cannot give you a detailed plan of it.
I mean, there's no government funding. It's all private.
Right.
We have never accepted any funding from any public body, and there's particular reasons for that, because I do not quite agree with the way this system is set up.
Well, I can be more specific about that. Government funding requires ownership, or at least half ownership, by the government agency of the IP, and they also want their business managers who play at being entrepreneurs with the full protection of a salary to actually manage the projects, and it just does not work. And that's why there's been $2.5 million spent by the government on 2 biochar chairs at Massey, and you ask them what they've achieved in 3 years, We've spent 310,000, and the result is what Wolfgang's now doing in India, and hopefully will do in New Zealand. So you asked the question, you take the
What
choice.
size materials going in at the front end? How big a material Wolfgang's going at the front?
The interesting thing when you run